Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Abdul Muhaimin bin Abdul Razak, B0422101111. I am the leader from Group K, and this is my group members: Iman Daniel bin Syarudin, B0422100062, Nur Atirah Nadia binti Al-Zahri, B0422100078, Aida Nadira binti Muhammad Jamil, B0422100078. Our group already done doing the laminar flow over the flat plate project using the computational fluid dynamic CFD. So and then we move to our introduction.
The topic for this video is laminar flow over flat plate. We use CFD simulation to simulate the action of fluid in laminar flat plate. We also use the method from CFD is boundary layer thickness. Before getting to know about how laminar flow over flat plate, we need to know and learn about laminar. Next is boundary layer. The layer of fluid in the immediate area of a bonding surface where the effect of viscosity are significant. The liquid or gas in the boundary layer take to cleave to the surface. Next, boundary layer thickness. The thickness of the velocity boundary layer is normally defined as the distance from the solid body to the point at which the viscous flow velocity is 99% of the free stream velocity. The surface velocity of in viscous flow. The boundary layer thickness increase, fluid particle velocity decrease, surface roughness increase, fluid viscosity increase. Next is theory laminar. If the flow is smooth and if the layer in the flow do not mix microscopically, then the flow is called laminar flow. In laminar flow, layer will glide over each other without mixing.
Next is theory laminar flow over flat plate. It is a streamlined, flat surface over which a fluid flows smoothly in parallel layers. Next is understanding the behavior of laminar flow over flat plate is crucial in various engineering applications such as aerodynamics and heat transfer, where the control and optimizations of fluid dynamics play a significant role. So the objective of this experiment is to study about boundaries layer thickness and laminar flow over flat plate, to find the velocity and thickness using CFD simulations, to learn how to use CFD simulation, and lastly, to learn the behavior of fluid flow near a solid surface. So CFD is a computational fluid dynamics, is a branch of fluid mechanics that use numerical analysis and data structures to solve and analyze problems that involve with the fluid flow. However, CFD is much more than just computer of numerical science. Direct number solving of complex flows requires an overwhelming computational power. Success in solving problems is very dependent on the physical model applied. This model can only derive by having a comprehensive understanding of physical phenomena that are dominant in certain conditions. So next is the reason we use CFD. So firstly, CFD is alternative to experiments that are expensive and time-consuming, and also the theoretical methods which can tackle only simple cases. CFD complements experiment and theory. And lastly, CFD is used design and development for research and in education.
Assalamualaikum. My name is Daniel. Now I will continue our presentation. So firstly, open the software workbench. After that, we will choose fluid flow, which is fluent. Then right click geometry. After that, right click new design modular geometry. Now we will start drawing. Firstly, go to sketching. Select the sketching. Then click show in 2D and snap. Change the value in major grid spacing to 0.1 meter. Change the minus step per major. Change the value to 10. Click draw and we will start drawing. Click rectangle. Start drawing at coordinate 0, 0. Pull the arrow to draw the rectangle. Click general. Click horizontal. Include the value 0.3 meter. Click vertical and include the value 1.5 meter. Then click SY plane. Click sketch 1. Click apply. Then save. Now continue with mesh. Right click. Click axis Z. Right click mesh. Right click insert. Select face meshing. Then click surface and click the object. Click generate. Right click mesh. Right click insert. Then select the sizing. After that, click edge. Then select the top and bottom of the object or diagram. Click apply. Change type to number of division. Change value of number of division to 50. Change behavior from soft to hard. Then click generate. Right click mesh. Right click insert. And then select sizing. Select left side of the object. Then click apply. Change type to the number of divisions. Change number of division to 60. Change from yes to no. Change to hard. Change from bias to the line dot. Include the value of bias factor to 70.0. Then click generate. Click mesh. Click insert. Then click sizing. Select the right side of the diagram and repeat the same steps like we do before. Apply, then click generate. Now click face and select the object and right click. Click create name selection. Type A_floor. Click name selection. Click A_floor. Click H, the left side of diagram. And right click, create name selection. Type the name is inlet. We will repeat the same step at the right side of diagram, at the top and at the bottom. At the right side of diagram, we will name outlet. The bottom we will name plate, and lastly at the top we will name far field pressure. Then click generate and we will save the project. Now right click mesh and update. Click the update. Now continue at the setup. Double click setup. Then click double precision. Choose 4 at solver process and click start. Now we will start. Click check, then click models and choose viscose. Change the viscose from SSTK omega to laminar. Click OK. Click material. Click air. Then change the value of density to 1. And change the value of viscosity to 1 exponent negative 4. And click change. After that, click close. Click boundary conditions, select and click the inlet. Include value of velocity magnitude 1.5. Click apply and close. Now click far field pressure. And change the type to symmetry and apply and click close. After that, go to method and change the scheme to simple. Then go to monitor, click residual and include the value for continuity, x velocity and y velocity. Include 0.000001 and click OK and cancel. Now go to initialization and change to standard initialization. For compute, select inlet and click initializes. Click run calculation and change the number of iteration to 1 million. Then click calculate and wait for the result. Now we will continue with solution. So firstly, we will click the graphic, then we will choose contour. right click contour, then change the from pressure to velocity. After that, we will click the banded, change from smooth to banded. Click save or display. Now we will continue to vector. Change the style to the arrow, then include the value of scale 5, then click save or display and close. Now continue with part 9, then select inlet and click save or display and close. Now we will save the project and select OK.
Next, we open the result and choose Z-axis. Then we choose contour and click OK. After that, the location we choose symmetry 2. And then apply. After that, number of contour 50, and then apply. Then the variable we replace to velocity and apply. Then we choose the chart and OK. Then the x-axis we choose the velocity u, and y-axis choose variable y, and then apply, and then just close. After that, we go to insert, location, line, and then OK. Then point 1 we change to 0.3, point 2 0.3, and 1.5. And sample we use 100 and apply. Then we choose the chart 1 and click for to data series, location, line 1, and then apply. Then the graph will come out like this. And then we save the project. Then I want to share about the result of data 1 and data 2. Velocity magnitude data 1 and data 2 show that fluid flow velocity increase and maximum. And because of the friction between fluid and wall, we find the fluid velocity is 0. Then the velocity plot for data 1 and data 2. Data 1 shows that the velocity u increase and stay constant at 1.5 meter per second, while velocity plot for data 2 shows that the velocity u increase and stay constant at 2.5 meter per second. Then velocity magnitude, relationship between result and theory. Velocity magnitude under laminar flow condition, this profile depicts the velocity distribution within the boundary layer. According to our contour, the fluid flow velocity increase and reach its maximum near the flat plate. So, velocity plot, the fluid velocity variation across the boundary layer from the plate surface to the free stream velocity is depicted by the velocity distribution plot on a flat plate. When a velocity map is used to illustrate laminar flow on a flat plate, it shows a parabolic curve that gradually increases in distance from the plate surface to the free stream velocity. Our findings indicate that the velocity plot diagram at y-m axis shows that velocity u increase and stay constant. That's all for result and theory, and that's all from our team, Group K. Thank you.